Okay, today we're going to talk about Kepler's laws of planetary motion. Johannes Kepler developed 3 laws to describe how the planets move around the sun. And in these 3 laws, you have the law of ellipses. His second law was law of equal areas and law of harmonic law. It's the harmony of the planets, I guess, as we may describe it. All right, so moving on. First law is on ellipses. We talked about this in class already the other day, and so I'm not going to go into much detail on I'm not going to go into any detail on the calculation of eccentricity and stuff like that, but because you guys already know how to do that. The orbits of the planets around the sun are ellipses or elliptical. It's said either way. Just understand an ellipse or an elliptical orbit. That right there, that's an ellipse. Okay, has 2 foci. That's what the second point is here, is it's centered on 2 foci, and you guys already know the sun is at one of the foci. The other point, okay, and I know this one's small here, but if you have 2 foci, if you can see these 2 dots that I have on here, one of those is going to be the sun, and the other one is going to be an imaginary point in space. I mean, I can't say it's an imaginary, there's nothing there. So you have the 2 points, but the sun is, or whatever it's orbiting, okay, is at one of the foci, okay? And the object that's doing the orbiting is going around on that ellipse, all right? Now, a high eccentricity. If something has a high eccentricity, it is close to 1, which I wrote this down because it's always written to 3 decimal places. Always write eccentricity to 3 decimal places, okay? 0.999. Okay, that's very close to 1. Very elliptical or very eccentric. It's going to be very stretched out, close to a straight line if it's a high eccentricity. Okay, if it's a low eccentricity, it's going to be close to 0.000, which is nearly circular, or really, if it's 0.000, it is perfectly circular. It's a perfect circle. But something closer to this. And if it is perfectly circular, it only has 1 foci. It only has 1 thing that it's orbiting. There's 1 planet that we have that has a very, very close to circular orbit. Okay, a couple of them. Venus and Neptune are very circular. All right, the second law. Kepler's second law is on equal areas. Now what we're talking about is the area that I shaded in right here. So when you drew this, or if you're still drawing it, make sure that, see how there's a bigger distance here and a very small distance there, because this blue line is the orbit. Right there's the sun at one of the foci, and this blue ellipse is the orbit of the object, of the planet. Okay? What it says is an imaginary line joining the sun to a planet will sweep equal areas and equal intervals of time, okay, or periods of time. As a planet moves closer to the sun, it moves faster. Look at, when it's close right here to the sun, if that's where the planet is in its orbit and it's really close to the sun, it's going to move faster, so it's going to cover more distance, okay, than when it's farther away. When it's farther away, it's going to move slower in its orbit, so it's not going to cover as much distance. But that area and that area that I shaded in green right here, those are equal. Okay? So, as a planet moves closer to the sun, it moves faster in its orbit, slower when it's further away from the sun. What month or what season are we closest to the sun? Ironically, yes, it's winter. Okay? You guys know because we've already talked about this. If not, it's a little bit of review. But in the winter, we're actually closer to the sun, but because of our tilt, that's why we're colder in the northern hemisphere. Okay? In the summer, we're over here. In the summer, we're farther away from the sun. If you ever notice this, the sun actually appears bigger in the sky in the winter and smaller in the summer. Okay? And it's all because of our proximity to the sun. Close to it or far away from it. Okay? Now, excuse me. All right, perihelion. Heli meaning sun, okay? Para means close. It's a point along the orbit when it is close to the sun, which I just put on here winter again. Okay, but para means close, so it's when we're close to the sun. Okay, we'll actually talk about this later. And with the moon, when we orbit the moon, you have para and then G, which geo is Earth. Okay, so para meaning close and heli for sun, or geo for Earth. What would we be talking about orbiting the Earth? The moon. Okay, so it works the same way. Just understand these words kind of go hand in hand. All right, aphelion. This might help you out a lot. The A is away. That's why I underline the A. It's a point in an orbit when it's farthest away from the sun. And I know it's tough to read it right here, but it says summer. Okay, so the aphelion is when we're furthest away from the sun in the summer over here. This is aphelion. This is perihelion. Alright, Kepler's third law is harmonic law. The time it takes a planet to complete one orbit around the sun is proportional to the distance between the planet and the sun. What this means is, if you're close to the sun, like this red circle right here, you're going to go around at one rate. You get farther away, you're going to go around a different rate. Sum it up. The farther a planet is from the sun, the longer it takes to go around it. So, this one's farther from the sun, it's going to take longer to go around the sun, okay, to revolve around the sun, okay, or orbit. If you're closer to the sun, it goes around much quicker. So the closer a planet is to the sun, the faster it goes around it, or orbits it, or revolves around it, okay. Do not ever use the word rotates, because it means totally something totally different. Rotating is just sitting and turning. Revolving is doing this, going all the way around another object. Okay, and in this case, we're talking about the sun. Okay, so you got a faster orbit here because they're close, slower orbit here because they're farther away from the sun. And yeah, that just kind of sums it up there. Okay, last thing I want to add here, we had the Kepler's laws, so he has his three laws, but then this also relates to the gravity, which is, gravity is what causes us to orbit another object, okay? So what affects the gravity between the sun and the Earth? Why is the gravity different between the sun and the Earth than it is between the sun and, you know, let's say Neptune, way the heck out there? But anyways, Newton's law, universal law of gravitation, the mass and the distance between the objects has an effect on the gravitational force, or the gravitational pull between them, how strongly they're pulled towards each other. Okay? Massive planets have more gravitational force. So the bigger the planets, or the bigger the objects, okay, the sun is the biggest thing in our solar system, okay, most massive. And so if the sun is the most massive, that's why we're orbiting it, is because the sun has such a great mass. Okay, the more massive something is, the better chance things are going to orbit it. Okay, why don't we have a lot of things orbiting the Earth? Well, we don't have anywhere near the mass that the sun does. Okay, so the moon got caught in our gravitational pull because the Earth definitely has a very large mass. Nothing compared to the sun, though. Okay, so I just wrote in here. Obviously, these are not planets. 500 kilograms and 500 kilograms. Just give you a number to kind of put it together. They're going to have a pretty strong pull. Well, a lot stronger than if you relate to 100 gram masses. If you have two objects that are 100 grams, okay, they're going to have a lot weaker pull. They're not going to be pulled together as much. Okay, so the more mass that an object has, or two objects have, the stronger that pull is going to be to pull them together. Okay, now planets that are close together have a stronger gravitational force. Okay, Mercury is the closest to the sun, so it's going to have a stronger force just because it's so much closer. Now, Mercury doesn't weigh as much as some of the other planets, so that makes it a little bit weaker just because of its mass, okay? But because it's so much closer, it also has a very strong pull, okay? Now, so if two objects, let's say that they're the same exact mass, two objects of the same exact mass are going to have a strong pull if they're close versus those same two objects being farther apart. So it's kind of a combination between the distance between the objects and the mass. Very massive, close objects are going to have a really strong pull. Very low mass, distant objects are going to have a much weaker pull. Okay? So, that covers Newton's law and Kepler's 3 laws describing how and why planets and objects orbit in the solar system.